So I want to present here a theorem from analysis called the spectral. Sorry, my spelling is spectral decomposition theorem. Okay, so an extremely important theorem, very easy to understand, but very important. And what does it say is that suppose that we have, we have a Hermitian operator, say O, with, say, eigenvalues OI with corresponding eigenvectors, or eigen, I should say not vectors, but eigen functions, psi I. What does it mean? When the operator O acts on the vector psi I, we get a vector back, the same vector back, but the constant of proportionality is OI. And this is the eigenvalue, right? So the set of eigenvalues of O is called the eigenvalue spectrum. Okay. So if we have this, then the operator O can be expressed, its matrix elements can be expressed as a sum, and the sum can be a discrete sum or a continuous sum, but let's just use the discrete sum notation, where we have the eigenvalues multiplying the complex conjugate of the eigenvector times the eigenvector with this x, and this is x prime, okay? So this is the spectral decomposition theorem, okay? So just to make it more, okay, in the continuous case, say in the continuous case, what we have is, say, O xx prime. This is going to be some d of, so my O looks like theta. So d O, and then O times psi star O of x psi of O of x prime, okay? So this is the, remember, just note that, the argument of these psi's are not the same, they're different, okay? So let's do some examples. Just 1 second. The easiest example is, say, let's take the identity matrix, and it's xx prime, the identity operator and the xx prime matrix element. And we know from previous lectures that this is just the delta function. Okay. But you know that this can be Just 1 second. Yeah, this is a kind of a trivial example, actually. Okay, let me come back to this a bit later. Let me give you a different example first. Okay, so okay, let's look at the P matrix, the momentum operator. Okay, so for the momentum operator, if you take the XX prime element, this is going to be H bar by I. So in one dimension, this is the derivative with respect to X acting on the XX prime, right? We know this. So according to the spectral decomposition theorem, we should be able to express this as a sum over the eigenvalues times the eigenvectors, right? Two factors of the eigenvector. And this can be done in this case because what I can do is an H bar I d by dx, I can express this thing as 1 over 2 pi H bar integral over d of p, and then I have e to the power I p x minus x prime by H bar, right? So this we can express the delta function like that. Okay, so then what we can do is that, we can take the derivative inside the integral sign, and then we have H bar by I. Here we have 1 over 2 pi H bar d of p. The derivative with respect to x will bring down a factor of ip over H bar, and we have e to the power I p x minus x prime as before. And now we see that H bar cancels out, and I cancels out. And then using the definition of EP, we can write this as integral over dp times p psi. So these are the, let's write this like this. Say E of P star of X, E of P of X prime, right? So as we see that this is exactly in the form of this expression. So we see that the theorem holds for the momentum operator, okay?
Should there be a 1 over H bar in the exponent?
Yes. Yeah, thank you. Okay, right? Okay, so let's carry on. So part of this observable postulate is that, when you make an observation of an observable, the result will be or must be an eigenvalue of the corresponding operator. Okay? So this has all sorts of consequences. Okay, so the mathematical structure that quantum mechanics inherits from linear algebra And it carries over to the case of analysis, which what we are dealing with, means that the observable that should say the complete set of eigenfunctions of an observable form a complete basis for the space of function of space of wave functions. Okay, and this is basically what we used because the momentum operator, its wave functions are its eigenfunctions are EP of x, and when we expressed any old wave function as a linear combination of, when we express this as a Fourier integral, which was 2 pi h bar square root cubed, and the integral of d cubed p, we were essentially using this fact. Okay. And this meant that at a later time, this would be given by, I'll come to this in more detail later. So this was at time t0. At a later time, this would be given by e to the power I by h bar p dot x minus et. Okay. So here we are using this axiom or this mathematical fact that the complete states, eigenstates of the momentum operator, they give you a basis for the whole space of wave function. So any wave function can be expressed as a linear combination.